we want to understand, we wrote the expression straight away, but let's understand how Fermi level changes in a extrinsic semiconductor. Okay, and we are assuming, let's say that T is equal to 300 room temperature. So let's start with first what happens if I introduce some dopants. Let's say ND, a donors I'm introducing. I introduce 10 power 3 per centimeter cube. So I'm introducing a very, very small amount of donors. So I have 10 power 22 states in my silicon lattice per centimeter cube, but I'm only introducing 10 power 3 donors. If I do that, what would happen? What do you think will happen? Well, even when I don't introduce, now your N naught is going to be basically your ND, which is the dopant introduced electrons, plus there's also going to be some contribution from Ni, right? You can think of it sort of like that. I mean, I'm just simplifying it a lot, but anyway, yeah, this is going to be roughly what it is. So it is still going to be Ni. It's not going to matter if you introduce very, very small doping concentrations. Okay, because 10 power 3 versus 10 power 10, so 10 power 10 is going to win, right? So it's Ni. So if you want to dope a semiconductor, you can't put a doping of 10 power 2 and 3 and expect something. But the range of doping that we have to do is something in the order of 10 power 15 at least. Okay, 10 power 15, let's say. If I take 10 power 15, what do you expect will happen? Now, it's going to introduce lots of 5 orders of more holes than what is there in the intrinsic, right? So now, in this case, simply N is going to be ND. Okay? So the donor atoms are going to dominate. That is the whole thing that will dominate. That will give you the electron. That's going to give you a lot of electrons. Okay. So now, what happens physically? You're putting lots of electrons here. Lots of electrons on this line, right? What happens to the Fermi energy, Fermi function? Fermi function should give you the distribution of electrons. So previously, there was equal probability of finding electron on the conduction band and a hole in the valence band. That's why the Fermi function was at EI. Okay, but now you have added externally a lot of electrons. When you add a lot of electrons, what you need to do is this Fermi function moves upwards now. So in some way, basically the distribution has to move upwards so that your EF, basically, EF is defined as the energy at which your probability is half. So probability half is what you need to care about. So since the more electrons have been introduced in the conduction band, the EF has to go higher. Okay, so higher means it's going to go towards the EC. Okay, so basically, what if you introduce now ND equal to 10 power 18, I increase the number of dopants. If I do that, EF is going to go further higher. Okay, so as ND increases, EF moves from EI. EI is basically the intrinsic level in the center, right? Where the intrinsic semiconductor EF is going to be in the middle of the band gap. From there, it starts moving towards EC. Okay, that's what happens. And that is why, when I said in the last N naught is going to be Ni times exponential EF minus EI. So when I introduce ND, when I introduce donor atoms, I know that my Fermi level is going to go upwards. As it goes upwards, this quantity N naught is going to increase. And that's what we know, right, will happen. So logically, you could think of it like this. Okay. So now what happens if N naught is increasing? What should happen to P naught? What will happen to the equilibrium density of holes? Okay. So to understand that, what we need to do is we have to also write P naught. Okay. So what will be P naught? P naught is going to be, well, yeah, let me come to it. Just let me take a slide. I'll talk of acceptors and then we will talk about this one more time. Okay. So let me put a divider. All right. So now let's think of what happens when you have acceptors. Okay. Same story. If Na is going to be 10 power 3, 10 power 4, it doesn't matter. Na has to be something large. Okay. So as Na equal to 10 power 15, let's say, per centimeter cube, then what happens? You're essentially creating lots of holes. This implies lot of holes in valence band, right? That means you're essentially removing electrons from the valence band. So your probability of finding an electron is going to come down. Fe has to come down. The Fermi distribution has to move lower. So implies EF has to move from EI. EI is your reference always, intrinsic. From intrinsic, as you add more and more acceptors, EF has to move towards EV. Okay. All right. So let me erase this and let me erase this. So you see, in intrinsic, this is basically Fermi level for intrinsic semiconductor. Okay. As you start adding dopants, let's say you're adding dopants, right? ND, you're adding dopants ND. As you add ND, you're adding electrons, and therefore EF moves this way. Okay. EF moves towards EC. Okay. As ND increases. Similarly, as you keep adding holes, or you're adding acceptor ions, if you substitute silicon atoms with acceptors, then you create holes, and therefore your EF should come down here. EF moves towards EV as Na increases. So this is how the Fermi level will move. Okay. So what will be P naught? P naught is simply going to be Ni is the starting point, and if the Fermi level moves below EI, P naught will increase. If it moves above EI, then P naught will reduce. Okay. So this is going to be exponential. EF is going to be higher now. EF minus EV. Sorry, I should not EV. I'm sorry. EI is going to be higher. So EI minus EF by KT. All right. So basically, as Fermi level goes closer and closer to EV, the term in the exponential will increase. The exponential term will increase, and so you get more and more holes. If the EF goes above EI, then the exponential term will reduce. So the P naught, the holes will reduce. Okay. So now let me see. Let's take a few examples. Okay. Okay. Let me do this. Okay. Let me just write down these formulas. N naught is going to be Ni exponential. I'm just repeating it because you should also get used to these formulas. Okay. EF minus EI by KT. And P naught is going to be Ni exponential EI minus EF by KT. Okay. So let's consider a situation where ND is going to be 10 power 15. Okay. This is an N-type. Let's assume an N-type semiconductor. Okay. ND is 10 power 15 centimeter cube. What will happen to EF? Okay. So what we can do is, what will the concentration of holes, concentration of electrons? Well, it's much more than Ni. So N naught is going to be, we can forget the expression. We can even say that it's going to be let's do this slightly differently. Okay. So we know this. So what will be the distance of where exactly will be the Fermi level? Okay. So we said for an intrinsic semiconductor, the Fermi level is at this point in the middle of the band gap. So if I add more donor atoms, where exactly will be the Fermi level? That's what we want to compute. So we want to compute, let's say it's somewhere, somewhere in the middle. Okay, it's going to be somewhere here for a N-type impurity. Okay, what will be the distance we want to compute? Okay, so this distance we want to compute. How will you calculate that? Essentially, this distance is going to be EF minus EI, right? To calculate this, what do we have to do? Well, we have the expression n naught equal to ni exponential EF minus this one, right? So whenever you have n-type impurities, we know that essentially those are going to contribute, right? Because intrinsic contribution is going to be less. The electron hole pairs from the intrinsic contribution is going to be less. So n is going to be nd, okay? If you're, this is a 10 power 15, so n is going to be nd, okay? And EF minus EI, I can simply take the logarithm of the expression on the top here. No? Let's call it equation 1. I can take the logarithm of equation 1. And so basically what I get is kt times ln of natural logarithm of n naught. N naught is going to be nd by, okay, we'll do it like this. Okay, this is the expression. Okay, all right. So now this kT is basically going to be in the energy units. It's Boltzmann constant times the temperature, but we have to write it in energy units. And we told you multiple times that this is going to be room temperature. It's going to be 26 milli electron volts. Okay, this is 26 MeV, 26 milli electron volts into, I mean, natural log is hard, so let's write it in terms of log 10. So log ND was 10 power 15. Okay. Now I want to make my life simple, so I'll say Ni equal to, I'm not taking the exact number, Ni is equal to 10 power 10 I'll take. Because if I take 1.5 extra, then I have to do exact with a calculator, which I don't have right now. So I'll simply take it as 10 power 10. If I do this, what do you get? Well, I sort of, have memorized this expression. This is basically 59 milli electron volts. Okay. So, yeah, 59 milli electron volts. Yeah, this is the number. So, this is going to be into log 10 power 15 by 10 power 10 is going to be 5 order. So, this is going to be 5. So, EF minus EI is going to be 60 into 5 is 300. So, minus 5. So, 295 milli electron volts. Or, you can say 0.3 electron volts. Okay. So, this is how you can calculate, what is the concentration. Okay. So, this is going to be what now? This distance we calculated is 0.3 electron volts. The whole distance is how much? This is basically 0.56, right? EV, because band gap was 1.12. So this half band gap, Eg by 2 is going to be 0.56. So we have sort of come halfway into towards the conduction band. If you dope 10 power 15, you have come halfway into the conduction band. Same thing you could repeat for 10 power 18. If Nd is going to be 10 power 18, what would happen? Now we have already done most of the calculation. So it's going to be 10 power 18 divided by 10 power 10. So 8 orders of magnitude. So I'll leave it for you to verify, but it's going to be 59 MeV into 8. That's going to be 60 into 8, 36, right? 36 minus 6, 354, 54 MeV. Okay, it's going to be 0.36 MeV, 0.36 EV. So as you increase, you see 10 power 15 was already at 0.3, but as you go higher and higher, the Fermi energy moves slower. It doesn't move as quickly as your concentration increases. Okay, this has some implications. We'll show you something in the end. Okay, so well, this is electron concentration. That's fine. What is a hole concentration? Well, hole concentration is basically going to be P naught is going to be Ni exponential EI minus EF by KT. Okay. So we can calculate it, but instead, I have a we can do a simple thing here. So we should remember always under equilibrium, N naught, P naught is going to be Ni square. You can verify this, okay? N naught, P naught equal to Ni square. So P naught is going to be, once you know what is N naught, P naught can be directly calculated. So yeah, I mean, bear with me. Now I'll do the exact calculation just for the heck of it, okay? So I'll say 1.5 into 10 power 10 whole square divided by N naught is going to be Nd. Nd is going to be 10 power 15, let's say. So this is going to be 2.25 into 10 power 5. per centimeter cube. So you see what happened. As you introduce dopants, n-type dopants, the equilibrium concentration of electrons increased and the equilibrium concentration of holes decreased. So that always, you remember this, you have to remember it very, very well, that N naught P naught equal to Ni square under equilibrium conditions. All right, this cannot be violated. All right, you could do the same math for acceptors. Okay, you could consider what will happen when Na, right? Let's say you put, then if you consider Na is equal to 10 power 15 per centimeter cube. Okay, so if you want to calculate Na, if you have acceptor impurities, your P naught is right away going to be 10 power 15 because most of them are holes you are introducing into the valence band. Okay, we don't have to, we can ignore the contribution we can ignore the intrinsic contribution. Okay. So P naught equal to 10 power 15. So from that again, if you do the same math, it will come out to be the Fermi level is going to be 0.3 below EI. Okay, in this case, let me just P naught equal to Ni EI minus EF is by KT, right? So EI minus EF is going to be implies, no, we did the math last time, it should be the same. So this is going to be 0.3 EV. So what this is telling you is, if you introduce acceptor ions, your Fermi level is below by a distance 10 power, not 10 power, this is going to be 0.3 EV. Okay. As you increase acceptor ions, your Fermi level has moved below. And if you take 10 power 18, what would happen? It will go to 0.36. Well, I think I took this expression is wrong because 60 into 5, 8 5 is a 48. So it should be wrong. Okay, I took it as 6 times. Okay, it's wrong. Okay, you just verify it. Okay, this is going to be 8 5 is 48, 6 is 48. 48 minus 6, so it's going to be 474, I think, MeV. Okay, this is going to be 0.48 EV. Okay, please check it out. Okay, and here also check it out. Okay, well, I'll put a question mark. I think that's what it should be. Anyway, yeah. So the same story repeats. Okay, and once you know P naught, what is the electron concentration? N naught. N naught is going to be Ni square by P naught. That's going to be 2.25 into 10 power 20 divided by 10 power 15. That's going to be 10 power 5. Okay. 2.25 into 10 power 5 centimeter cube. Okay. So remember now, let's summarize this. Okay. You have N type and P type. You have Nd equal to 10 power 15 per centimeter cube. Here Na is equal to be 10 power 15 per centimeter cube. All right. So then this implies N naught is going to be 10 power 15 per centimeter cube. I'm just leaving it out. Okay. P naught is going to be 2.25 into 10 power 5. Here P naught is okay. Let me not write it like this. Let me write it in the expression form so that you can use it. This is going to be Nd. P naught is going to be Ni square divided by Nd. Here, P naught is going to be Na, which is basically you're introducing acceptors, so you're going to be having Na, and N naught is going to be Ni square by P naught. So, in an N-type semiconductor, we call electrons as majority carriers. Majority carriers, right? Because those are the ones which have the highest concentration. And the holes are called as minority carriers. You see the numbers if you had calculated, right? This was 10 power 15 and this was 10 power, it was 2.25 into 10 power 5, right? So you see majority carriers are the most significant number. The concentration is high. Minority carriers are smaller in concentration. Similarly, here it was 10 power 15 and this is 2 into 2.5 10 to the power 5. So if you have p-type semiconductor, the majority carriers are holes and minority carriers are electrons. All right. So this is the distinction between n-type and p-type. All right. Let's see if it works. Yes. Okay. All right. So you can use this as a reference. You can calculate multiple times, just try out some examples. All right. So, well, yeah, I just wanted to show you a few more things wherein we calculated this already. So as you increase your doping, this is a graph of EF versus doping. Okay. So if you have n-type semiconductor, okay, this is an n-type semiconductor. When you have n-type semiconductor, as the doping Nd is increasing, as the donor concentration is increasing, your Fermi level starts out closer to EI, right? This is EI. You can call it EI, EFI. I mean, they're all same. Okay. So it starts closer to that, and as you increase the concentration, it tends to move towards the conduction band. The opposite behavior is shown by the valence band. So it starts out at closer to EI and then moves towards the valence band. Okay. I want you to actually note you see this distance here. The question here we can ask is, can EF touch EC? Or here, can EF touch EV? Okay. So essentially what we are saying is, if you keep doping high enough, can the Fermi level go further? Because it seems like saturating, but will it go further into the conduction band? There is a very long answer to that. It will actually go into the conduction band or into the valence band. That's possible for EF to go in, but these expressions cannot be calculated with the expressions I have given. These concentrations, or these EF levels, Fermi levels, cannot be calculated with the expressions I have given you, because the expressions that we have shown in the class today are only valid for what is known as degenerate doping. Okay, so the degenerate doping means you have the distance between EC and Fermi level has to be greater than 3 kT at least. Okay. Similarly, distance between Fermi level and EV has to be greater than 3 kT. 3 kT is basically going to be roughly 75 or 75 milli electron volts, 0.07. Okay. If the EF goes closer than that, then the expressions we have used break down. The approximations don't work anymore. So we will not get correct results. So we will not even bother. Okay. There's no point in calculating, you could put 10 power 19. We can check out how much is, please do that as an exercise. Take ND is going to be 10 power 19. Just take it that way. Okay. For this, calculate EC minus EF, how much it is. Okay. Or, you can calculate this and see what happens. If the EC minus EF is smaller than 3 kT, then the calculation is not going to be correct. Okay. I mean, you'll get some numbers, but they're not going to be correct, okay, because the approximation we make in that case is actually breaking down. All right. So, well, let me just give me a moment. Yeah. So I thought of doing a few more things, but it looks like I'm running out of time. So I just want to summarize now. So what we did today is we introduced the Fermi function. We talked about the probability of finding an electron at a particular energy level, which is essentially the Fermi distribution. And then based on that, we defined the Fermi level for an intrinsic semiconductor. Once we did that, we understood what happens to Fermi level as you change doping. We tried to take some test cases, if you have dopant, n-type dopant, what happens to Fermi level? If you have p-type dopant, what happens to Fermi level? And we calculated that. So that's what is summarized on this slide here. So please take your time and try to figure out how to write these equations correctly. So in your exams, it can be, multiple forms. I mean, you can solve a problem in many different ways. Whatever works for you. I mean, there is nothing like a right way or a wrong way. Okay. So it's going to be fine. As long as you get the correct answer, it's fine. So you can use this expression, or you could use n equal to nc exponential. That also will give you the same answer, because you know how much is nc minus ei. So you will get the same answers, but whatever is convenient for you. All right. So please, whenever I show you the summary slides, please make sure that you are comfortable with the information provided on the summary slide, because that will be useful in the next couple of lectures. Okay. So with that, I would like to stop here today and have a great day. And I look forward to seeing you in the next lecture.